So, then welcome to lecture number 1 in the introduction to Lattice Boltzmann method in winter 25-26. So if you were able to read my mail, I've sent you a link to a video of the broader introduction on Lattice Boltzmann. So it's not required for understanding this lecture here, but because we had one missing lecture, I sent you this video for an overview, and now we step directly into the theory. So today we will not talk about the Lattice Boltzmann method, but about the theory on which the Lattice Boltzmann method is more or less built. This is the kinetic theory. So kinetic theory is something, so the word kinetic is used for a lot of different things. So you may know about robotics, and there you hear about kinetics, and you may know about chemical reactions. There is a kinetic, and then there is physical kinetics. And if you look in the physics books, this is usually, for example, Landau-Lifshitz. Do you know Landau-Lifshitz? Theoretical physics. Okay, I know one of you is smiling. Yeah. So this is. Some people say that's the most important physics book written. A little bit of problem is it's relatively old, so it's not up to date. But so there is everything to the middle of the 20th century. What was in physics has been written in the series of books, and their kinetic theory is volume 11, so the last one of the last chapter of classical physics is kinetic theory, so to speak. Okay, so what we want to do with kinetic theory in the end is to describe matter, of course, and for this, even if you don't know kinetic theory, you will know about two different ways how you can describe nature. Yeah. So on one end, you know that nature, so that physics, yeah, is made out of atoms, and these atoms, they interact with forces. So each atom is an individuum, if you like, and all of them interact with forces. And then we have another end where we describe matter as a continuum, and we describe them by differential equations. Right? So these two things you know, and surprisingly few people think about the problem, why can both of this be true, and why can I use differential equations to describe nature when nature is actually built of atoms? Yeah? Because if it's made of atoms, then it's discontinuous. And if it's discontinuous, you can't use differential operators. Yeah? So this is something that should actually bother all of us. And the thing that connects the two dots, yeah, the atomistic world and the macroscopic world, which in a sense are both true, they are connected through the kinetic theory. So the kinetic theory is somewhere in between, and you could see this as follows. So you have these atoms, so individual atoms, and instead of taking individual atoms, you describe the state of matter as a probability to find a particle in a certain state, instead of following all the particles. Yeah. So it is and this is a probability. Yeah. So I mean, we can describe here the state of this lecture hall like, so you are coming, and I can also describe it in the opposite way, saying what is the probability that somebody is coming to my lecture, right? So usually it's easier when there are very few people coming to my lecture, then it's easier to describe them by the individual. Yeah, so this is like if you have very few atoms, then the most appropriate description of this system of very few atoms is, of course, looking at the individual atoms. But if I have a larger class than these, yeah, so, and I see, so what is the probability that this seat will here be taken, yeah, in the lecture, so then it becomes more appropriate, I mean, more efficient in a sense, yeah, just to describe, so what is the probability that 30 people come to my lecture, or something like this. So, okay, you can go from individual particles to probability of particles, and this is the kinetic description, and then what you can do statistics on this and take so-called moments. This is something we'll talk about in this lecture series a lot. And for these moments, you can actually write differential equations that you know. So this leads us to these three different types of equations that we can solve. The first one would be Newton's equation, where you have just forces acting on particles, interacting. So interaction between particles. So there's a particle I and a particle, and there are particle J's, and they are acting with forces. On the other end, we describe the world with the Navier-Stokes equation. So I hope, guess, or I don't know, are you familiar with the Navier-Stokes equation? Yeah. And in between is this Boltzmann transport equation. And the Boltzmann transport equation is what we are talking about today. The Boltzmann transport equation is also related, the Lattice Boltzmann method is related to the Boltzmann transport equation. Yeah, I cannot say it the other way around, because the Boltzmann transport equation is a big, physical important thing, and the Lattice Boltzmann method is just a numerical method to solve this. Yeah, that's of course this here is the more important thing, but we'll spend one lecture here on this equation and the ramifications of these equations for physics. So then we come to the actual lecture. We have the Boltzmann transport equation. So the important thing is, in comparison to when we talk about molecules or atoms in an atomistic sense, yeah, there we distinguish between these different atoms, and here we just talk about probability of finding a particle, and this means that the molecules we are talking about, they are indistinguishable. So this means we don't care which atom this is. So my not so nice comparison here ever, because this of course is not, because you guys are all individuals, obviously, yeah? But if I would just care, there are so many students instead of having individuals, yeah? So for atoms, or for molecules, this is often a pretty good assumption, because nitrogen molecules are much less different than people to each other. So we just ask for the probability of finding a nitrogen molecule there, not which nitrogen molecule this is. And if you accept that you just ask for any instead of for a specific, then you immediately see that you reduce the amount of information that is in this question a lot. Yeah. So So this I write this in caps because this is the very important thing here. So this probability, the one particle probability distribution, F, is then a probability in a velocity, a microscopic velocity that we call xi. My xi is not very beautiful, I'm sorry. A position x and time t. So this is a 7-dimensional probability, yeah? So the probability density, to be more precise. So this is the probability density function of finding a particle in velocity. So velocity is now a state. You're in the state of a certain velocity, yeah? Velocity, so xi. So I write down how I'm expressing this, yeah? So I will use xi, the vector xi, and the components of this I will write as xi without vector. That's the first component. This is the x velocity direction. Then I'll use an ugly upsilon. So these are the last letters of the Greek alphabet. So this is an ugly small upsilon and an ugly small zeta. Okay? And you, of course, you can write them beautifully. Yeah. So, and we are in location. We are in location x, which I will write as x, y, and z. And of course, it's time t, which is then one-dimensional. So this is what we are talking about. We have a probability of finding a particle. So, and for this, we have this Boltzmann transport equation that was written up there, and I will rewrite it here. So we have a change of this probability. So this is what is kinetic, whatever we call. So kinetic has many meanings, but what they always have in common is that it is a change, so that there's a dynamic or changing from state to state. Like you have these molecules, you have a reaction, then you have other molecules, or you have a robot that is standing like this, and then it's moving, and so it goes from state to state. Yeah. So transition is the word. Yeah. Kinetic is a transition from state to state, and here's a state of probability, and this is transitioning in time. So this is the change in time. Then comes so-called, I have a problem with this Windows 11 because it does not allow me to put the this bar somewhere else. I heard that there is a hack to do this. I will find this out. Because I am not allowed to touch my screen. So then comes this part here. So the velocity times the spatial derivative, so scalar product on nabla. This is, when you're already familiar with the Navier-Stokes equation, then you will see that this here is an advection term. Then there's something that we'll spend not a lot of time with. This is if there is a force, then this force acts like this, that we have, so we have the force, and we've normalized this by the mass of the particle, and we have to multiply this by a strange thing that I now call nabla xi, which is the derivative in velocity space, right? So we don't spend a lot of time on this. This year will be relevant for long range forces. So this can be electrical forces or, for example, gravity or something like this. This would end up here, right? So, and then we put everything else into this thing called omega here. Sometimes it's also called S. And this is the collision. And the collision is something like short-range forces. So these are forces that act when bodies touch. Yeah. So these are short-range forces. Okay. So let's talk about these individual parts one by one. I have to change the page. Okay, I'm not talking about the change in time. Yeah, so this is change in time. Yeah. So we talk about the advection. So what is actually advection? We have a particle at a position x and say this particle has a velocity xi. Then, after some time, because it has a velocity, it's moving around, yeah, it changes to position x plus delta x. So it changes here. So, and this delta x, because it is moving with this velocity, and now we are assuming there are no other forces, so just this movement, yeah, or, okay, let's say, because it's infinitesimally short, yeah, we can say that this dx, so even if there are forces, they don't have time to act, right? So we have dx is then xi, the velocity, times dt, or you could say that xi is of course dx by dt, which is the definition of a velocity. Now this xi is the so-called microscopic, so the word microscopic is here important, peak velocity, which is different from the velocity that you have in the Navier-Stokes equation. What you have in the Navier-Stokes equation is the macroscopic velocity. The microscopic velocity is the velocity of this individual particle, yeah? Molecule moving around, and this can also go, so when we have, when we have a wind flow, or I open the window and air is coming this way, so there's still not all particles going this way, there are some particles going the other way, yeah? Otherwise I cannot infect you with corona, yeah? So this is now important to understand this difference between this in the Navier-Stokes equation, where we also have an advection. Advection in Navier-Stokes equation. So what is advection in Navier-Stokes equation? Here we have the so-called material derivative, right? So we have, again, a change of velocity, the primitive variable, or the, what's it called, the dependent variable of the Navier-Stokes equation is velocity and is pressure, right? So we have the change in velocity plus this u times, so scalar product on nabla on u, yeah? So basically this is what we call the advection term in the Navier-Stokes equation. And this guy contains the dependent variable twice. Yeah? This is why the Navier-Stokes equation is nonlinear. Yeah? So because this is here dependent variable, so it's very important. Dependent. So I'm always telling the bachelor students the important thing with differential equations and other things you have to have a good understanding what is the dependent and what is the independent variable. There are inverse problems and optimization problems where, they often turn around, yeah? But you have to distinguish between them. So this thing is nonlinear in its dependent variable u. So this is causing problems for solving the Navier-Stokes equation. Okay, the Boltzmann equation. The Boltzmann equation, we see is describing the same thing. But it's a bit different. So we have dt f, differential t f, and here comes xi. So xi is also, u is a velocity. So xi is also a velocity. So it's driven by velocity. Yeah, it's the same thing. And this f, this is of course a function of velocity. Yeah, so this is a function of velocity. Because velocity, microscopic velocity, is a state. So this is an independent variable. Yeah? So this is the important difference. In the Navier-Stokes equation, velocity is a dependent variable, and here it is an independent variable. Yeah? Please. Yes, please.
What do you mean, actually mean by state? That thing is still a bit unclear.
Yeah, the states, yes, so the state is there are seeds, yeah? And I could now, you are in your seat, right? So, but I can turn the thing around and say your seat is in the state of being occupied, right? So finding a particle in a velocity state means that there is, we describe all possible velocities that a particle could have as their state. And if a particle then has this velocity, then it is in that state. Yeah? This having velocity as independent variable means that there's all possible velocities that exist, right? And then we have to find the particle in this huge space. We have to find where this particle is, right? So this xi is, I write it down. This is the independent variable. So now we are trading one problem for another problem. Huh? Here we have nonlinearity. Here we have linearity. Now we have a linear advection term. Therefore, we have all possible velocities. Yeah, we go from a 3-dimensional space to a 7-dimensional space. Okay. So it's interesting, yeah, because we are describing the same thing either with a nonlinear equation or with a linear equation. Of course, if you know something about mathematics, you know that the Boltzmann equation cannot be entirely non-linear, because if it was entirely non-linear, you cannot turn it in a non-linear system. You cannot transform a linear system in a non-linear system. That doesn't work. Yeah. So there is something non-linear in the Boltzmann equation too, and actually this comes with the collision. So collision, and we make here an important assumption, which is that only binary collisions exist. So binary means there are two particles meeting and not there are three particles meeting at the same time. This is less of a burden than it may be, yeah, because we are looking at extremely short times, yeah. Okay, to be absolutely accurate, it is a big burden, but in a very complicated way. So if you have looked at my previous lectures on this, I often don't make a lot of changes, but sometimes I make a little bit of changes. I had the impression that my picture that I had there last year was not completely accurate. So if anybody here looks in multiple cases, then you may be seeing something new. So suppose there are two particles coming this way and this way. Yeah, and we call this state, because they have not yet collided, we call this pre-collision. Pre-collision. So then I would say the first particle comes in with the velocity c1 and the second particle comes in with the velocity c2. And then they collide, and so it is difficult for me to draw physically correct. Yeah, I'll just do it a little bit with fantasy. Yeah, so they are not going exactly the same way. Say this one is the C after the collision one, and I will indicate that it's after the collision with this, tick here, and then the other one. So would, I don't know what makes sense. Say the other one may go this way. Okay, it doesn't. Maybe it's not accurate, but I only wanted to indicate that they go in a different way, right? And we call this after, this is the post-collision, because this happens after collision. So, and this is so complicated to draw because we are in the laboratory frame. Yeah, so say I'm standing here on my desk and I'll pick out two particles in the air and see how they collide, right? So this is not very efficient and a little bit problematic for me. I don't really know how to draw this, so it's easier to write this in the center of, to draw this in the center of mass frame of these two particles colliding, because then when we are in the center of mass frame, what this means, even though I'm not drawing it very beautifully, what this means that both particles will have the same velocity and they will collide head on, right? And so they have the same velocity, so I can indicate this, even though it's not beautiful what I'm doing. Oh, it's very ugly what I'm doing. Okay, I'm not getting it much more beautiful. Yeah. So this is supposed to be a circle. Yeah, and this is the center of the circle. And now the outcome will be the same. It will just be turns. So they will also end up on the circle, and they will not head on but tails off, right? So this. And this actually looks like this, yeah. So it's much easier to draw. So this here again would be C1, now in the center of mass coordinate system. This here will be C2, and the other one here would be, it doesn't matter, C1 dash and C2 dash. And this we call the center of mass frame. So it's much easier to do to work in the center of mass frame. This is something that we'll observe here. So why does this outcome looks the same as the and as the ingoing. This is to do with the conservation. Okay, maybe I should ask you some question. What things are conserved in this picture? Yeah, momentum. I mean, this is not the first thing that is conserved. This is actually the second thing that's conserved. You know, the number of the particles. This is the first thing that is conserved, and with this actually also the mass. So we usually start with the mass. M1 plus M2 is M1 plus M2 dash. So, because we do not distinguish between particles, actually. Okay, I mean, in principle, it is possible that particles exchange something, yeah, and that only the sum of their masses is conserved. And we don't have relativistic effects or atomic decay in here because we are in the last chapter of classical physics, as we said. So this is not happening here, but mass is conserved, right? But in principle, they could exchange mass, but because we assume these particles are the same, they are just 2m, right? So then, as you said, there is momentum conserved. So momentum conserved basically means that the length of the arrows, the combined length of the arrows is the same. So momentum is of course mc1 plus xc2, yes, is equal to mc1 after collision plus xc2 after collision. So that's not all that is conserved here. What else? Energy. So energy is of course 1/2 m, and then we have the square of their velocities, right? So this is xc1 times xc1 plus xc2 times xc2 is the same thing after collision. So we have xc1 dash times xc, so ugly x's, xc1 plus xc2 dash, so scalar product c2 dash. Okay? There is dash. There is something else conserved, which we are not concerned with. Due to the symmetry that this happens in a plane, also the angular momentum is conserved. But this is kind of not considered here. This is geometrically conserved. Yeah. Okay. So this leads us to the way how Boltzmann tried to solve this. So I mean, it's not actually clear what happens here, right? As you have all these particles, you actually have to look at the individual particles in order to see what would happen, but now you have only probabilities. So how to deal with this? So Boltzmann came up with something that goes very strangely by the German name, which I write a little bit further here. I mean, Boltzmann, of course, wrote his paper in German, so, and he used this word Stoßzahlansatz. I hope this is very self-explanatory to everybody in the world. And because so in translation, yeah, lost in translation, in the international literature, this is called molecular chaos, which is the same thing describing in a, I mean, the two words don't have anything to together, yeah, but they are somehow meaning the same thing. So Stoßzahlansatz is the ansatz that everything only depends on how many collisions do you have in a given time. Yeah? So everything is dependent just on the number of collisions, while molecular chaos means, okay, there is no correlations between these collisions. So both of them mean the same thing, because if you say that everything just depends on the number of collisions, then you forget about correlation. So it's meaning the same thing, but two different aspects. So it's actually useful to write both here. Yeah, it's molecular chaos and Stoßzahlansatz. So the molecular chaos part of this idea is that the velocity of particles colliding do not depend on each other. So, and if you went to school and learned statistics, and we are talking about probabilities, then you should say this is wrong, because what are you doing? You pick one particle from your distribution, and then you pick another particle from that distribution. So what you should know is, if you pick one particle and you want the other one to collide with them, it cannot collide with itself, right? So you have to pick another particle. So you have changed the distribution. By picking one, yeah, you change the distribution. And Boltzmann said, well, I'm picking one particle from a very large distribution. So it does not change, okay? But this is an assumption, and this is wrong, and would be visible wrong if there are few particles, yeah? But because there are many particles, this is a useful assumption, okay? So, yes, and the other part is that only the number of collisions influence the behavior. We want me to use British or American English. And there's the, okay, write it like this. So let's use a simplification for describing all of this. We use a parametrization. Parameterize, okay. Direction with a directional vector. So there is the sigma of length 1. So we only specify that it has length 1, nothing else, yeah? Such that this xi1 dash can be described as xi1 plus xi2. No, we are not assuming that we are in a center of mass coordinate system, because we put here the center of mass. So we can be in any frame of reference, right? It's center of mass. And then we add to this the difference between their velocities. I mean, it makes sense that collision depends on the difference of velocities of the particle, yeah? And multiply this with this directional vector. And then, so these are all the pre-collision situations, and this is the post-collision for particle 1. And then we write the same thing for particle 2. So there's again, we have the center of mass, which is the same as in the other case, divided by 2. And now I made the one mistake that I was not supposed to do. Okay, we know that when one particle because this is we put the center of mass in one place and then the in center of mass part in the other place, so that we know that when one particle goes this way, the other one goes directly in opposite of, right? So this means that we have the second, when we have a plus, then the other one is going with minus. So then it's xi1 minus xi2 divided by 2 times sigma, okay? So now we can describe our collision just by sigma. And what can happen? So when two particles collide, it is completely coincidence, yeah, in which direction they go off. So they can go off in any direction. So we don't know this, yeah. So when this means for the collision, we want to describe the collision, then we have to, because the collision only changes, again, the probability of finding the particle after the collision somewhere, then we have to integrate over all the possibilities in which they can change, right? So, and also we have to do this, of course, for all the different states with which they could enter. So let's say we have this omega, no, I should, wait, just wait. I should write the collision integral, yeah? Okay, talking about collision integral. So we call this collision integral omega. And this we can write also like this. So this is the change of the probability density only due to collision, meaning not due to streaming, to advection. So that would be, as I said, we have to integrate. So we have to integrate over all direction. We use this sigma to indicate the direction. So all directions would be integrated by capital sigma. So this is all directions that could happen. Then we have to, so we are looking for the outcome of xi1, which will collide with any xi2, with a particle having any xi2. So we'll have to integrate over all the xi2, yeah? So, okay, I hope you recognize this is supposed to be a capital xi2, yeah? So we go over all directions, all possible directions. And we go over all velocities of the second particle, yeah? So then comes something that I'm not going to explain in a lot of detail here. That's called the, so there's a kernel function that is related to the what we call the collision cross section. We call this, yeah. So this is basically so when particle gets close to each other, the probability that they collide and how they collide depends on how large they are, right? And also a little bit it depends on how fast they are, because there are actually some forces acting, yeah. And so actually when they fly faster, they have a slightly smaller cross section, yeah. But that's not something that we want to talk about a lot here, yeah. So this is basically this cross section, and this can be a function. It just can be a function of the difference in their velocities, and it can be a function on the angle by which they hit, yeah. But so it's just a function, and then it depends on the presence or absence of the particles. right? So in order for particles to collide, there must be, so the one must be present and the other one must be in this particular other state. And this is, okay, so there are now two terms, and let me see. So for mathematical reasons, I write the other one first. So there is a state where they end up with. Yeah, so after collision, they go to a new state, and this new state is now the probability after the collision for the position of particle 1 in this velocity state, and the probability for particle 2 after the collision. So this is after collision. So I only write this first because I don't want to have a minus and then the plus here, because then, okay, I should. Unfortunately, this type of lecture where equations usually don't fit in one line, right? So there is there's the second term. This is xi, so minus the one that goes in. So why do we have minus here? So this is before collision. So why is the one minus and the other one is plus? This here is a gain term, right? So something is coming into the state. Yeah, so this is positive. Yeah, so this counts positive for a change of f. Yeah, something is put into the new state, while this here is a loss term, not to be confused with machine learning loss term. Yeah, we were first. Kinetic theory were 150 years before machine learning. Yeah, so this is the loss term. And this, so what you could understand here, so two particles collide, so they are put out of this state. So you could imagine this like the particles are destroyed in this state and re-originate in another state. Yeah? So they disappear here, where they originally came from, and they re-originate in this other state. So we have to subtract the previous state and add the new state, right? And then we have to integrate this over all the velocities and all the directions. Okay, I see different levels of confusion in your faces. Everybody following?
I think the after collision term should be 1 xi prime 1 prime times f xi 2.
Yeah, that's obviously true. Yes. Okay, so this indicates, so there are two particles. Yeah, if we had three particles, we would have had three of them. So this is the indication that there are two. Okay. By the way, I have to admit, I don't know whether this is the good place to point this out, but this is not necessarily a very easy lecture. I mean, a very easy subject in all of this. Yeah, I hope this should not discourage you to come here and try to learn this, but this is a very advanced lecture. Which, if you don't get everything, then please still come. Yeah. Okay. Okay, just a few words here about the collision. The collision kernel B, which we call the collision diameter or cross section, or what's This is a function of the relative and so in kinetic theory, you know, we talk a lot about how to actually get this cross section, but this is not our primary idea here. So gain and loss. Gain is particles scattered into the state C1, so the velocity again is the state, and the loss are the particles scattered out of C1. Okay, so this thing has to fulfill conservation laws, obviously, the ones that we have seen. Conservation laws. I mean, you see the integral, it's not very obvious how to solve it yet, right? Don't come to this lecture. We'll have to wait for next week to see how this can actually be solved. So, okay, we have mass, momentum, and energy that we want to conserve. So what does this mean? This means that the collision, this omega, is not allowed to change mass, momentum, and energy. And if it's not allowed to change it, this means that the integral over now all the entire distribution that we deal with. This is now not Xi1, but this is not Xi2, but Xi1. Yeah. So if you integrate over all the incoming particles, then this omega is not supposed to change them. So the integral over this is 0 together with a kernel that goes over Xi1, and this kernel, so with the kernel, this phi is an element of either 1. So if it is 1, it's just the integral over the collision operator, meaning that all the particles going in are the particles going out. So this will give us the conservation of mass. Yeah. So, but also, if this phi is the velocity Xi1, yeah, so that means that the momenta, the integral of, so if I integrate over all the velocity states, so I get the momentum of my system. And the collision is not allowed to change the momentum of my system. So this integral with, when I multiply with the collision operator with Xi1 and integrate over all velocities, it should also be 0. And the same thing is for energy, and energy is Xi1 into itself. Yeah. So when phi is this, it will also be 0. And for other things, this will typically not be 0. So these are the conserved moments, as we call them, and other things would be non-conserved moments, because something has to change during collision. Yeah, otherwise there's no collision. So now is the question: do you know what moments are? So we're coming into statistics here. Yeah. So integral of distribution f, so any distribution with a kernel with a kernel phi is called a moment. So who of you hears about moments for the first time in their life? I should ask, so, okay, who of you know what moments are? Why is this? Okay, so this is a funny thing. Yeah, so actually we have two empty. You should either know what moments are, or you should not know what moments are. Yeah, and you prefer not to. You know, this comes from Corona. Yeah, so everybody, even so people, loss of interaction. Okay. If you don't know what moments are, you will know what moments are after you've finished this lecture, because we're talking about moments every Tuesday now, okay? So this is very, very important for us here. So there are obviously five conserved moments of the collision integral. By the way, the collision integral is not the integral that we have here. The collision integral is this omega, yeah? So we integrate the integral, okay? That's the point. And so five conserved moments of the collision integral. Yeah, and we could also say, we also call these things collision invariants, because they are conserved, they do not vary across the collision. So, and these are somehow related to the primitive variables of the Navier-Stokes equation. Because they are scaled moments. So we have the density. Okay, so we are a little bit flapsy with this. Okay, I still call it density. Density rho, yeah, so this is if you integrate, actually in order to really have a density, you would also still have to divide them by a finite volume, actually. Yeah, but this is not done here. There is one annoying thing in kinetic theory, is that we sometimes use a little bit shortcut notations, such that our equations don't necessarily look like they are dimensionally consistent. That unfortunately happens here, because this is a very specialized field, and the same thing happens if you, for example, know concrete chemistry. Yeah, they only care about calcium, the stuff that is in there. Though they write calcium as C, for example. Yeah, because they don't have anything else there. Yeah, so okay, it's maybe a little bit inaccurate. Yeah, we call this the density if we just integrate over the entire distribution function, and this we call the zero order moment. The zero moment, yeah, because we have the velocity to the power of 0, right? So the first is when we have the velocity to the power of 1, and then we end up with the velocity, but as I said, there's something scaled here. So we have to divide by the density. So if you interpret this as mass or density, but you have to divide by this, and then you can integrate again over the same thing, C1, doing xc1, and then you multiply this by xc1 dxc. So if you integrate the entire probability function with their velocity, so you get the velocity of the system at this point, and this is the velocity in the velocity field of the Navier-Stokes equation, right? So these things are clearly related. So this is the first moment. First moment, and then we have, so now it depends what, we could now do several things here for the second moment. I'm lazy and talking, okay, it's not this lazy. We'll understand this a little bit later. I now call this temperature, and in my notes there's just, I call this just T. I should probably call this T K Boltzmann. Yeah? So what is K Boltzmann? The Boltzmann constant. The Boltzmann constant is the relation between the kinetic energy in 1 degree of freedom and the temperature. Right? So the temperature is energy per degree of freedom. Yeah? So then actually I call this kBT, and then we have 1 divided by rho by something annoying that's called d, and this is the number of dimensions, so it's 3. And we live in 3 dimensions, and integrate over xc1 f xc1. Now things get a little bit annoying because we are talking now about temperature. So temperature is the kinetic energy, but the part of the kinetic energy that you can measure in the centered frame of reference, right? Yeah? So there is the kinetic energy of so you would not call the kinetic energy of the storm that is currently in, where is it, hitting the, so in front of, America, is it in Cuba or something? No, it's not in Cuba. Anyway, yeah, so there is a storm again. Yeah, so the movement, the kinetic energy of this, you won't call this its temperature. Yeah, so you would subtract this, and only the part that is in the centered frame of reference you would call this the temperature. So what you have to do here is you have to take C1, you have to subtract what you'd measured as the macroscopic velocity, and then you have to square this. So there's this scalar product into itself, minus u, yeah, and then you integrate this over xc1, and then you have a second moment. So you see, this is kind of a second moment, but it's also a little bit more complicated. So what I cannot write here is, okay, I will try to put this in this last corner here. So these 3 is the number of dimensions. Because temperature is per degree of freedom, and this thing has 3 degrees of freedom. This is why we have to divide by 3. Okay, so now we come to the interesting part of today. And okay, we come to the interesting part after introducing this. Now we want to understand something about, okay, physics in general, and the second thing, how this integral actually behaves. So we have to understand one thing to be able to understand how this integral will behave, but the thing is actually much deeper than that. And now we come to the so-called ether theorem, which some of you may know as the H theorem. So who of you heard about either the H or the ether theorem? Let me see whether the guys in online lift their hands. No? Okay. Okay, so there is a historians debate whether this letter is called H or Isa, because H and Isa, capital Isa, look the same, and we have only Boltzmann's writing, we have not his works. So in the international literature, this is usually called H, but everybody who can read Boltzmann in the original usually assumes that's more sounding like he is using Isa, because he is talking about something kind of related to an energy. So because we are here in Germany, we are going to call this thing here eta, okay? And we call this thing Isa theorem, and there will be at least once today say H theorem just as accident. So this thing is a very important principle of nature, and if there had been a Nobel Prize for Physics before Boltzmann died, which was in 1906, then he would have gotten this Nobel Prize for discovering the H theorem, because it's one of the most important and has the most profound implications in physics, one of these things. And here we'll need this. Okay, so we need this to see where the collision is driving the distribution of the particles too. Yeah? The question that Boltzmann asked is, what would be the state in which further collisions would not change the system any further, right? So this was the idea, and we have given this thing a name. So when the collision does no longer change the distribution, then we call the system to be in equilibrium. Yeah. So if this is like when I look at my desk and throwing new stuff on my desk doesn't change anything anymore, then my desk is in equilibrium. Yeah. My desk is always close to equilibrium. What did I write? When the collision does no longer change the distribution, okay, it is said to be in equilibrium. And we would be able to solve this integral, at least approximately, if we knew what this equilibrium is. So now, how do we find out what this equilibrium is? Let me see whether we can do this in 20 minutes, otherwise it will take a little longer. So first thing is, because I have to write a lot now, this is a lecture with long equations, because I have to write a lot now, I will define F1, F as this Fc1, yeah, and I will write F1 dash as Fc1 dash, okay? And then we are looking at our integral, at our collision integral that I write, so that we already had, but I write this again because we need it, as equation 1.1. So the collision integral is this, the change in the population in the population just due to collision. Yeah. So I write all of this in a little bit shorthand format now. I just write B, not what it depends on. yeah, and I write F1 and I have equilibrium times F2 dash equilibrium. So this is the gain term, and then we have the loss term, F1 equilibrium times F2 equilibrium, and this we integrate over Xi. Sorry, this is Xi2, and over all directions, and this is now supposed to be 0, now by definition. So if we are in equilibrium, collision should not change it anymore. Yeah. So then I say this is so I have to find this state. So what Boltzmann then did is something extremely clever and something very difficult to explain. Namely, he defined eta of t, so this is changing in time, to identify the equilibrium. So, and now how did he define it and why did he define it like this? So if we had more time, because actually I find this really, really fascinating, the history of, let me write it down. I personally find this very fascinating. Maybe I'm boring you with this, but during the time when Boltzmann was active, yeah, so Boltzmann was at the University of Wien in the late 19th century, and one of his colleagues there was Ernst Mach, and there were arguments on the philosophy of physics. Yeah, so there is, if you have ever heard about the Wiener Kreis, Wiener circle. So they basically invented they followed a philosophy of positivism. This means that you always had to base your theories on actual observation. And actually, much later, so like 60 years later, there was another professor there, and it was Karl Popper. Anybody know Karl Popper? Okay, he is nodding. Yeah, Karl Popper was actually in a different field, but he's a philosopher, and actually he finished. So out of the interesting thing is that the positivism killed itself. So they positively declared that they were wrong. Yeah. So actually, and Boltzmann did this in a completely different way. So he set up this function, and now you can ask me, so Ernst Mach would and probably had asked, so how do you come up with this function? And I now declare is absolute. So I cannot explain why he came up with this function, and it doesn't matter at all. Yeah, it's just there is a function that has a certain property. And we look at this certain property now. Yeah? And then, it's not important where it comes from. It's just that there is this function. Then you can write down this function. So what do we do with this function? So first of all, by the way, okay, one thing is important. This function, so we integrate over Xi1 now. Here we integrate over Xi2, right? So we integrate over Xi1 and we integrate over the entire space. Meaning this integral, I mean, it's very philosophical anyway. This is an integral over all microstates, so all velocities. And all coordinates. So this means it describes something about the whole universe, okay? So we are not thinking little here, we are thinking extremely big. Yeah, so this applies to the universe. It's a property, H is a property of the universe, okay? So, now what we are going to do is we look at a time derivative of this thing. So how does this thing here change in time? So we take the time derivative of this guy, and this gives us, so we put the time integral inside the time derivative inside the integral, and probably this is how Boltzmann came up with this equation, but we don't know and we don't care. So we put this here, C1. Okay, I should probably, I just said that I don't write C1, now I write C1. dx1 dx. So what we are going to do is now we're using the chain rule, right? To express this. So we'll have this integral, and we applying the product rule on this, yeah. So we have the first one, d by dt, f, okay, now let me write it f1, right? f1, and this goes multiplied into logarithm of f1, and then we have the second part, so this is f1, and d by dt, the logarithm of f1, and we integrate this over c1 and dx. Why do I write 1 here? So there's only 1. Okay. So, so here we apply obviously the chain rule on the logarithm, and this gives us, so the first thing here will stay the same, dt f1 log f1 plus f1. Now, okay, if I apply the chain rule of this, I get, 1 over f1 and d by dt f1, and I integrate this over c1 and dx. Okay, so then what? I have this. I have this time derivative here twice. Okay. So I'll take out this time derivative, d by dt f1 without bar, and this goes into 1 plus log f1, and this is integrated over c1 and the entire universe. So now this is the time derivative of this ether, and the ether theorem now says that the ether theorem is dh by d. Now I said it, yeah. d ether by dt is smaller or equal to 0. So this is for physics. It's not very common that we have a theorem. In physics, we have theories. A theory is something that you cannot disprove, or that you were not able to disprove experimentally, and the theorem is something that is mathematically proven. By the way, that it's mathematically proven does not mean that it is true. It means that if the universe behaves according to Boltzmann equation, then it would be true. I mean, because it's mathematical proof always needs axioms. Yeah, so it's only inside this space it is proven, but there it's proven. So we call, so then, okay, if we have this thing that there is something in the universe that only moves in one direction and not in the other direction, yeah? Then this here defines what is the direction of time. So actually before this we didn't know what time is. Yeah, now we know what time is. Yeah, because there's one thing in the universe that always goes one direction and it goes always forward and never backward. Okay, well, and when it's no longer moving at all, then we say we are in equilibrium. The equilibrium is when ether does no longer change in time. So you could now see, because this is about the universe, so the universe apparently is going one way and will be in a state in which it will be dead, if the theory is true. I mean, the theorem is true if the theory is true, right? Because the theory is a model. So why is the theorem true? So now we have to see why this is true. And we see this by inserting the collision operator or the collision, I should not call this the collision operator because I haven't called it this way. So I should call it collision integral. We often call this collision operator is again something that is coming from the nomenclature of, it's not mathematically very accurate. So, okay, again, d ether by dt is, now we have this guy here, and this is our collision operator, yeah? Integral, yeah? So, this we can replace by b f1 dash f2 dash minus f1 without dash and f2 without dash. And here we have what else we have, plus logarithm 1 plus logarithm f1. And we integrate this thing over xc1 and xx. So do you already see why this is supposed to be 0? Probably not yet. So let's go on and see something else. So we always look at what is particle 2 doing to particle 1. But we can also exchange this, and this should be the same thing. This is symmetric, yeah? We look at what is particle 1 doing to particle 2. This should follow the same equation. So in fact, we have f1 and f2 are interchangeable. New page. So they are all interchangeable, so we write down equation 1.4, so that d ether by dt is the integral over the kernel and f1 dash f2 dash minus f1 f2, and here we have 1 plus now log, we are exchanging them, so it's f2, right? And now we have to integrate over okay, I made a mistake. Who saw this mistake? Here, with the integrals, yeah? Because the integral, so the integral, this temporal integral goes over xc1, but the collision integral goes over xc2. And because there is no xc2 in this, I can put this to the end, right? And then I have to integrate over xc2 and also over all directions. Okay, so these I've forgotten here. So we'll put, and it doesn't matter in which order we have them here. So it's right xc1, xc2, the x, and all the directions. So, okay, we integrate over everything that we can integrate over. So now we have ds2, and what we can do now is 1.3 plus 1.4. Bear with me, yeah, this will be very interesting. And this gives us 1.5, so we add both of them together, so we have twice the change of the of eta. And here we have b f1 dash f2 dash minus f1 f2, and here we have 2 plus, so, and now I write the logarithm. So we add the logarithm of f1 and the logarithm of f2, and you notice that we integrate over the entire thing. So we always integrate over everything. So now all of you see that we can write this as logarithm f1 and logarithm times logarithm f2, right? Yeah, because the sum of the logarithm is the product of it. Okay, and then this is dx1, dx2, dx, and the sigma. So, now we are kind of a little bit stuck, but there is a very important assumption that we do now, and this is a very crucial and interesting assumption. What we are assuming is that our collisions are symmetric. Yeah, so that, I mean, they also look symmetric. Yeah, we have a loss term and a gain term. So when they come in like this and they go off like this, they could also come in like this and go off like this. So meaning we can interchange pre and post collision. And keep this in mind because this is very important. So we are assuming collision is symmetric, is reversible. Yeah, meaning if we turn, mind the contradiction, yeah? If we turn all the particles around, everything would go backward. Yeah? And we are proving that everything goes one way, okay? So, how is this supposed to work? Okay, let's see. So collision is symmetric. So then can go forward and backward. Forward and backward. Meaning what we are doing is now we are exchanging f1 dash f2 dash with f1 and f2. So, okay, so this gives us 1.6. I'm a little bit, okay, this, talking about the length of this lecture. So we will have some exercises later, so that not today, but that will take longer than 1.5 hours altogether. Yeah, so it's not. I have, because I think you get a lot of points for this. So it's not just a lecture. So I typically may take a little bit longer because it's now 4:30, obviously. Yeah, but when we have exercises, it will take longer anyway. IRMB here. 2 dh d eta by dt is b. So now we turn everything here around. So we do just the exchange. Loss term becomes gain term. And we have 2 plus log. Now also here we have the post collision guys here. Xi1d, Xi2 x and sigma. So now we have it backward and forward, and what we do next is we take 1.5 and add 1.6. Now we have the entire thing 4 times. D isa by dt, and now we have b f f1 dash f2 dash minus f1 and f2. So I follow up this, and we notice there is a change in sign here. Yeah. So obviously, if we have change in sign here, so the 2 will drop out, and we'll also have a change. So we'll have the thing up here, so the logarithm of f1, f2, and down here we'll have, because we changed the sign, we'll have logarithm of f1 dash, f2 dash, and then we go to dxc1, dxc2, dx, and overall d sigma. So, and this is smaller or equal to 0. Why? Anybody sees this? Hmm? Yeah, so what's about the log term? The log term, sorry for my childish cartoons, the log is monotonic, right? So meaning that if f1, f2 is either larger or smaller than f1, f2 after collision, then this also implies that then this is also the case for the logarithm because it's monotonic, right? So then f1 dash, f2 dash, now it's the opposite. This is smaller or larger than log f1, f2. So what do we have? We have here the post-collision minus the pre-collision, and here we have the, okay, I mean, we could actually put this entire thing into the logarithm, yeah, that, no, we cannot, no, sorry. So, but, so if this thing here is larger than this, then this is positive, right? But then this here is larger than that here, and then the entire thing becomes negative. And if it's the other way around, then this is negative and this is positive, right? So no matter how it is always negative. So now you see by just this algebra we have proven that d eta by dt is smaller or equal to 0. And as I said, that ether defines the direction of time. So what I find really absolutely fascinating is that the assumption that we used to prove this is that the collision itself is reversible. This was the assumption that led to this. So reversible collision lead to irreversibility of the universe. So last thing to say is, okay, now, yeah, okay, one thing more. The system approaches equilibrium, and equilibrium is where this d isa by dt is equal to 0, and we'll look next week and what this means for how we can take the equilibrium out of this. This ether is kind of a scaled negative entropy. So unfortunately, the entropy is something that was known before Boltzmann, yeah, but we can connect this actually to this. I mean, it was known before we know that there are atoms. We already had entropy before we knew that we had atoms, yeah. But Boltzmann actually connected these two dots again with this ether, but he used the strange definition of this so that it's not exactly the same and it has the wrong sign, if you will. Okay, so that's about the lecture. I will close the recording now, and then I may say something else.